So this little chunk, we're gonna, again, talk about how units are all related, all connected, and using our integral to help us solve these problems that have a rate, and then you want to come up with a total, okay? And it all has to do with how units are connected. It's our last thing that'll be on the quiz this time. All right, so let's again just review what we've talked about for units and how, in my mind, these are units in the way they go down because I think of them as division. Okay, if you start with meters and then you take a derivative, that takes you down to meters per second. If you take a derivative again, you're dividing again, and you end up with meters per second squared. And then we've talked about how to go the other way, how to go up. Okay, and so the answer to how do you go up is by using integrals, aka antiderivatives. And that's how you're going to go up in terms of units. So I want you to even think, like if you're going up the ladder or up the stairs in terms of units, what would be like up here?
Nothing.
Oh no, there is something. It's the opposite of what you've been doing. So think about how your units are going down. Not meters squared. It's not the meters has been the same. It's been meters, meters, meters. The meters is staying the same. What's changing? The time part. The time unit is changing. So we've got time squared, second squared. And then in the middle, we've got time to the first power. And then meters has time to the 0 power. There's not time, but then what would it be?
Meters time.
Yeah, it ends up to be meters times seconds. Okay, the multiplication would happen there, which has implicit meaning. You get into physics. I was talking about that with some of them last week. We get into things called like foot pounds. It's a foot times a pound. Or, you get into joules if you're taking physics. Things what joules mean, okay? Newtons, you get into newtons. Okay, those are the newtons and joules are all multiplication of units, okay? All right, so our integral is what we call an accumulator. An accumulator means you're adding up a lot of things. Remember, how many things are we adding up? Infinitely many of them. All right, and we've used the accumulation means the sigma. So this accumulation is the Greek sigma. Sigma needs to accumulate or to sum up together, but we're doing the limit as the number of those would be approaching infinity. That's what the accumulation is. We can do that with velocity, but we can do it with any units. It doesn't just have to be velocity, okay? It doesn't have to be a rate in terms of physics. It can be a rate in terms of biology or a rate in terms of economics or a rate in any of the rates that we've done. So if you want to find out the accumulation of something, it will always be an integration. Integrate it. If you're looking at any kind of rate and you want to find out the total, it's always going to be an integration to take care of the units. All right, so the definition. If you can integrate it over a closed interval, then it will become what's called an accumulator function. So our first example is just water being pumped. So water is being described, and we take a look at the units here. The units are gallons per hour. That's our unit. And we identify the time that's happening for an interval of 3 hours. So find the accumulated total of the water over the course of that 3 hours. So because we're dealing with gallons per hour and we want to find a total, that would be an accumulator, we simply set it up as an integral. So you write the integral, you indicate the time from 0 to 3. The function is WT. And then because we're talking about time,
DT.
It's dt. All right, so that is what's required for you to just write down the proper integral. Now it comes, am I doing this by hand, or am I doing this by geometry, or am I doing this by a calculator? And so if you're doing it by hand, then you're going to maybe approach this as an antiderivative. So then I set that up, okay, so now I'm gonna do this by hand. And so I find my antiderivative by hand. Remember, you announce an antiderivative first with a bracket, and then the antiderivative would be 1/4 of t to the 4th, or t to the 4th over 4, however you prefer to write it, minus 1/2 of t squared, plus the constant 2 times t, plus a constant c going over that time interval. And then we start plugging in our values. So we'll start by plugging in 3. That'll give me 81 over 4. And then I plug in 3 again. That'll give me 9 over 2. Then I plug in 3 again. I'll get 6. Then I have a plus c, and I have a bunch of zeros, and then I have another c. So I have plus c, and then minus 0, and minus the other c. So the c's are going to go, oops, and the 0 does nothing. And then I would probably get all my common denominators so that I could figure out, that's the easiest for me. I'd have 81 over 4 minus 18 over 4 plus 24 over 4, which turns out to be 87 over 4. And what are the units on that? Why gallons?
Yeah, because you took out the.
Because the original units were gallons per hour, and integration takes out that time, and so I have 87/4 measured in gallons. That's the total amount of water added into this tank. We've kind of dabbled with this already a little bit. All right, from the 1970s, from 1970 to 1980, potatoes were consumed at the rate of an exponential rate of millions of bushels per year. And then key here being that T are the number of years since the beginning of 1970. And so then how do you write the number of bushels consumed from 72 to 75?
2 to 5.
Okay, all right, so I want you to think about, what is it really 2 to 5? It's the beginning of 1972 to the end of 1975. How many years is that? All of 1972, all of 1973, all of 1974, and all of 1975. It's all the way from one to the other. So it is not from 72 to, it's not from 2 to 5.
2 to 6.
It's got to be 2 to 6. Let me see if I can argue my way to that. Okay. This says you have to do the beginning. Okay, so you can't say from the beginning of 1972 to the end of 1975. You have to say from the beginning of 1972 to the beginning of something else. If it's defined in terms of beginning, then everything has to be, your units have to be in beginning as well. So the end of 1975 is really the beginning of what? 1976. It's only one day apart. Okay, so you have to adjust so that they both say the beginning of something. From the beginning of 72 to the beginning of 1970. So it's really only 1 second difference we're talking about, because the end of 1975 would be December 31st, 11:59 p.m. And then, 1 second later would be the beginning of 1976. So you are setting this up as 2 to 6. Watch the time units. Make sure that your time, how it's described, is matching for yourself. And then you can put C of t dt. Now you could do some of this by hand. It wouldn't be pretty, but it is possible, because you know how to do the antiderivatives of the number 2.2. So it could be by hand. That would be 2.2 t. And you could, yeah. No. And you can do the antiderivative of 1.1 to the t. What kind of function is that?
Exponential.
It's exponential. Do you remember how to do the derivatives of exponentials? So the derivative would have been 1.1t times what? the natural log of 1.1, and then also times, which is just 1. Okay, so if I'm going to do the antiderivative, I do the reverse. 1.1t divided by the natural log of 1.1 and the number 1, which is irrelevant, plus c. Yeah.
So the denominator, you would just multiply it. Like what if it was 14?
Yeah, so then it would be times 4, and typically what I would do, Ethan, is I like to put my 4 in front. I think it looks nicer to have 4 natural log 1 instead of natural log 1.1 times 4. That's what I would do. All right, so we'll take those away because they're not really there. Okay, but you'd have your calculator to finish that out. I'd probably let you have your calculator the whole time, so you can just do a math 9 on this to evaluate what the value is from 2 to 6. All right, so grab those calculators. Make sure the mode is irrelevant right now, but let's evaluate this. Rose is surmising that a multiple choice option would definitely be the people who do 2 to 5. Okay, 100%. That's going to be one of those options. All right, let's see. So evaluating this, 14.692 is what I get. All right, now what are the appropriate units to put on that? Is that how many potatoes are consumed? Okay, it's not even how many bushels. Okay, it's how many millions of bushels. You know how big a bushel is? Okay, imagine it's about the size of a basketball hoop, because they literally, that's how basketball was invented. They took baskets that looked like that and they hung them up on their barns, and then they shot in and they cut the hole out and the ball would go through. So that's why it's called basketball. Okay, but it's about that size. Right? That's how big a bushel is. And so, but we're not even just talking about 14.69 potatoes. We're not talking about 14.69 bushels of potatoes. We're talking about 14.692 millions of bushels.
Do you have to be like consumed from the beginning of 1972 to the end of 1972?
Of potatoes.
Oh, okay.
Okay. Oh yeah, if we're doing consumed from the beginning of 1972 to the beginning of 1976, or through that time interval or something like that.
Would it be wrong to write the end of 1971?
No, you can write it as it was. But it would be wrong to do this. It would be wrong to say from 1972 to 1975. That would be wrong.
Yep.
It's not from that to that. Okay. So not that. All right, try another one. Okay. Let's get some physics words into here. Okay, displacement versus total distance. The word total being key here. We've already talked about what the word total means. The total means you need to throw absolute values around anything that's negative. And so the same would be true if you're dealing with rates or negative bushels or whatever. Okay, negative dollars. If you're talking about total, you have to include an absolute value around the negative. If you're worried about it, you could literally put an absolute value around the whole thing, or even like that, and then then you've got the whole thing covered, and you're for sure gonna get that right. Okay, so displacement is different than a total distance. Okay, so again, I know I've told you this example before, but I always just think about running around the track out at the field. Okay, if you start at one spot and make one full loop, your displacement is nothing, because you have not changed. Your beginning and your starting position are the same thing, but you're feeling it because you just ran 400 meters, okay, or 800, 400. What is the track? 400, yeah. So your total distance is 400, even though your displacement is 0. That's the difference between total and displacement. Okay. Now, this is the one that usually trips people up. When then the follow-up question would be, what's your final position? Okay, your final position is relative to where you're starting. A lot of people assume incorrectly that the starting position is always 0. Sometimes your problem is going to have you starting somewhere else. Okay, you're starting at -5, or you're given a head start and you're starting, what if you were starting 100 meters ahead of the person ahead of you? Okay, your final position is different, not just the same thing as your displacement or your distance. It is the combination of your starting position and your displacement. So I think of this, can you think of other examples in calculus where we've had to look at two things and can then make a judgment call? Okay, like what? Okay, so you needed to know how it was changing. Okay, any other examples? Yeah.
When you're going forward or backward.
Okay, what two things do you... Okay, yeah, either forward or back, or, okay, so...
You need to know your origin and then whether you're,
Like your position.
yeah, your position, whether it's like positive or negative, and then your velocity.
Okay, so that was comparing velocity to its position, right? And there was another example. Okay, who hasn't done Lauren?
Over and under estimates, comparing concavity and increasing.
Okay, that was another one. Okay.
Speeding up and slowing
Speeding
down.
up and slowing down, you got to compare velocity to acceleration. So this is another example. You can't just base your answer on one thing. You can't just say the displacement is 70, so my final position is 70. Because your final position depends on where you started. If your displacement is 70, but your starting position was 20, then the combination of those two would give you a different final position. So you need to make sure you're combining those two things. All right, so let's kind of go through it all. Let's say we have a nice velocity equation, 10 minus 2t. Beautiful linear velocity equation, measured in meters per second over the time interval 0 to 9. All right, so we're going to put it all together. When is the particle moving right? When is the particle moving left? When is it stopped? What's the displacement? And then I've got part C and D on the next screen. So we're going to do this all. This is first semester, second semester, all combined. So how do you tell when the particle is moving to the right? What is the velocity doing?
Increasing.
Okay, the velocity is not increasing. That would be meaning that something is accelerating when the velocity is increasing. What does it mean when the particle is moving to the right? The velocity is positive. The velocity being positive and the velocity increasing are two different things. Because you can have negative velocity that's increasing. Those are two separate things. Okay, what does it mean when the particle is stopped? Okay, let's start there. I like to start with when is the velocity, when is it stopped? Right, so if we're working on part A, I'm going to take my velocity, which is 10 minus 2t, and figure out when the velocity is stopped. So it's pretty clear that the velocity is stopped, or the particle is stopped, where? At time equals 5. Okay, that is when the particle is stopped. So around that, we need to figure out what's going on other than the particle. So these are our good friends, the intervals that we did so much with first semester. So I'm going from 0 to 5 and 5 to 9. And what will I be checking within this interval?
Positivity or negativity.
The positivity and negativity of what? Of the velocity. Have I done any calculus yet? No, I haven't needed, because what did I start with? I started with velocity. So I haven't done any calculus. I don't need calculus yet. I just need to pick a number in that range. So I'll pick, 1, 2, 3, or 4 probably. And I end up with a positive expression, positive value. And then if I pick 6, 7, or 8, and then plug that in, I get negative. So I can identify that it's moving then to the right from 0 to 5. And to the left from 5 to 9. Notice that I don't have equality lines underneath it, because when it was equal to 5, it was stopped. It wasn't moving to the right or to the left. I did not ask you to justify your answer why, but you should still be able from first semester to justify why that's true. It is stopped at time 5 because the velocity is equal to 0. It is moving right from 0 to 5 because the velocity is positive, and it's moving left in that interval because the velocity is negative. Now we're ready to do displacement. So the definition of displacement doesn't need absolute values. The definition of displacement would go from 0 to 9 of the velocity equation. And you have the capability to do this. You have the knowledge to be able to do this 3 ways. You can do it antiderivative, you can do it geometry, or you can do it math 9. Okay, this is a simple 10 minus 2t is just going to be a linear line, so the geometry would be easy. The antiderivative is pretty easy. And then math 9, you could check your answer. So we would go 0 to 9 of 10 minus 2t. And let's assume we don't have our calculator, so you have your choice of whether you want to draw this as geometry or whether you want to do it as an antiderivative. Okay, if you do antiderivative, 10t minus t squared plus the constant c from 0 to 9. That's probably what I would do. And then I'm going to drop my 9 in there, so that'll give me 90 minus 81 plus c minus 0 minus c. So I end up with 9. Then I need units on this. I should have done units on my other one. 5 seconds, 0 to 5 seconds, 0 to 9 seconds, and the units on this are going to be meters. Okay, any questions so far? Yeah, Izzy.
When you're doing your, setting up the intervals for B, do you have to do the very first part where it's like V of t? Can you just skip to plugging in the function?
Mm-hmm.
Okay.
There has to be an integral that's set up though.
Yeah.
Like one or the other. I did both, but you could do one or the other. Okay. All right, so now we get to the part C and D. If S of 0 is 3, that is the starting position. So that means at time 0, the starting position is already at 3. So now I'm going to answer the final position, which is always a combination of the starting position plus the displacement. So my part C would be my final. By definition is starting plus the displacement. So that means I'm starting at 3, so I have a head start. I'm adding the displacement of 9, so my final position is 12 meters. If I'd started at a deficit, if I'd started at a negative starting position, I'd have to include that with my displacement. So what's the only time displacement and final position are actually the same? When you're starting at the origin, we're starting with the time value of 0. All right, then finally, find the total distance traveled by the particle. So that's part D. So my total now changes to an absolute value of v of t dt. So let's assume again, I mean, a calculator can do this easy peasy, but let's assume that we are doing it without our calculator. There is no antiderivative for an absolute value, aside from your calculator can do it. We have to approach this from a geometric standpoint in order to do the antiderivative. All right, because when does this thing stop being positive? At 5. We already answered that in a previous question. This thing stops being positive at 5. So we would need to split this up. And you know that's legal to do that with integrals. So going from 0 to 5, I can just do 10 minus 2t without worrying about absolute value because I know it's already positive. But I know that from 5 to 9, I'm going to have a negative number. So how do I make it positive?
Go the opposite other direction.
What do you mean?
From 9 to 5.
Yes, make it 9 to 5. That's one way. I could go 9 to 5, and then then I'm guaranteed positive. Can anybody else think of a different way they may have done it? Christian?
Instead of addition, you can subtract.
Okay, what do you mean?
Instead of adding the two integrals, you can subtract the second one. So subtract
Okay, so you're saying leave it 5 to 9, like that, and subtract. Okay, anybody think of another way to do it?
The same but factor negative 1 out. Or put a negative off 1.
Okay.
Keep it what you said.
I think what you're saying is leave it addition, but if you're factoring a negative out, make it 2t minus 10, which is accomplishing the exact same thing. Instead of 10 minus 2t, 2t. So there's several different things you could do to make sure that that part is positive, but you've got to address it somehow. You've got to make sure that section of it is positive. So whether you want to do subtraction instead of addition, whether you want to switch your bounds, it is totally up to you. Okay, I like switching my bounds, so that's what I'm going to do. I'm going to go 9 to 5, and I'm going to keep it 10 minus 2t. So my antiderivative, 10t minus t squared plus c, that one goes 0 to 5. And the same antiderivative, 10t minus t squared plus c, that one's got to go 9 to 5. So it is totally up to you, the method of how you want to do that. Just make sure you account for it somehow. So that's going to give me 50 minus 25 plus c minus 0 minus c. And the other one is going to give me 50 minus 25 plus c, and then minus 90 plus 81 minus c. I've already distributed my negative. I did that already. So the zeros don't matter. A couple of the c's. So I've got a 50 and another 50 and a couple minus 25s and then a minus 90 and then an 81. So you can kind of clump your math together. I do 50 and 50. That's 100. And then minus 25 and minus 25, that would be minus 50. And then the minus 90 and 81, that's minus 9. So what's our total answer? 41, and then meters. Okay, look at the total look at the difference. Like, we ended up with a displacement of 9, but a total distance of 41. So that tells me, if I only had a displacement of 9, but a total distance of 91, that tells me that my thing is going quite far forward for you guys, that way, and then coming backwards too. Not quite as far back as it went forward, but it went forward for a while and then backwards. All right, any questions on that? Okay. All right, last one. We'll do the same type of questions, just with a parabola this time. So the linear one was nice, but here's our parabola. So you should be able to do the same thing. You should be able to address when the particle is moving to the right and when it's left and stopped. I always start with stopped. And so in my part A, I would set 10 minus 2t squared now equal to 0. So if I solve that, where will this be stopped?
Plus or minus.
Okay. Okay, yeah, plus and minus rad 5, that's good, but I don't need the negative one because it's not in my time interval. So yes, good thing to think about it. So it's stopped at time equals the square root of 5 seconds. So then I would need to address what's happening before and after. I know what a parabola looks like too. So I know that when it's stopped, this is going to be a max. I should also be able to think about that. That could be very easily a follow-up question. Well, if it's stopped at rad 5, what's happening there? Okay, well, rad 5 represents the position of a max because this parabola is changing from positive values to negative values. I know what a parabola looks like. In my head, I can mentally picture that this parabola is going down like that, and so it's crossing from positive to negative at that number. So you should just kind of be thinking, I got to keep that stuff fresh for myself too. And then it's going right from 0 up to that rad 5 seconds. And then it's going left from that rad 5 seconds to the rest of the interval, which is 9. And again, why? And you should be able to justify that. My displacement, by definition, will be the straight integral from 0 to 9 of 10 minus 2t squared dt. So see, Izzy, I started just with that. I didn't have to, but. So my antiderivative would be 10t minus, now this is a little different antiderivative than we had before. this will be 2 divided by 3 t cubed plus c going from 0 to 9. So that's 90 minus 2/3 of 729. That's 9 times 9 times 9. Plus c minus 0 minus c. Now 729 does reduce nicely by 3. So I can do some math to help me out there. Okay, that reduces into 3 into 7. That's 2. 43. So 90 minus 486. So this answer is going to be significantly negative. Okay, 90 minus 486. So 394 meters. My last 2 questions are the same as they were before. What's the final position then?
Wouldn't that be negative 396?
What did I do wrong?
I think it would be.
Yes.
No. The last number shouldn't change, was the 10.
No.
That's what it says on the graph.
Yeah, 96. Sorry. I'm doing it as if they were both one of a positive number. Oops. I can't erase it. I don't know why. That's a 6. All right, and then we're going to add 3 to that number and come up with our final position. Total would be absolute value, so you have to set up your integrals, breaking it up at rad 5 instead of positive 5.